In Unit 2, we're going to be focusing on bivariate data. It's actually kind of brilliant that the College Board called this Unit 2 because bivariate data is just looking at two variables at once. Did they intend it? I don't know, but we can maybe give them some credit for being clever. Now, I'm going to be using data that I collected from two different places, Census at School and data.gov. I put all of the data sets that we might be using in the Google Sheet right there, so you can make a copy if you want. I'm just going to open it up and show you a couple things, and then if you would like to mess around with any of the data, you absolutely can. So we're going to start with two categorical variables because we've actually done that already. So if I go to Scatterplot, same website we were using in the last unit, I can choose two categorical variables. And let's just take a look. When you look at the spreadsheet, there's lots of different data sets along the bottom. Right now I'm just looking at American cars in 2004. So car type, there's an example of a categorical variable. We've got regular, SUV, sport, wagon, minivan, pickup. Another one that might seem quantitative, but I think could actually be considered categorical is number of cylinders. It's true, it's a number, but there's only so many numbers that you can pick. You're not going to have like 3.5 cylinders. And I will admit I'm not a car expert, but here's what I did. I went to Scatterplot and did two categorical variables. For explanatory, I put in the type of car. I think that would tell you how many cylinders the car is going to have. Maybe I'm wrong, and maybe the number of cylinders tells you the type of car, but sorry, not sorry if I got it wrong. So I put type as my explanatory, number of cylinders as my response. And these three types of graphs should be very familiar after Unit 1. We've got the side-by-side bar plot, or bar graph. You can see that the minivan has 6 cylinders more frequently than others. We've got the segmented bar graph. That's where you take the side-by-side bar graphs and put the bars on top of each other. I don't know why some cars have -1 cylinders. I feel like that is a typo. And then we also have the mosaic plot, and remember that's basically the segmented bar plot, but the bars are proportional. So there are more regular cars than minivans and pickups, and I can't even read those because it's so smushed. So those three should be very familiar. For two categorical variables, we could make a side-by-side bar graph, we could make a segmented bar graph, or we could make a mosaic plot. Now, if you're taking notes along with this video, you might just want to do a sketch. At the bare minimum, just write down the names of those types of graphs. Now, we can also look at one quantitative variable and one categorical variable. For this one, I want to look at a data set that's not quite as overwhelming. So this first one is about diamonds. I forgot to mention that in each sheet along the bottom, I've copied an image just showing you like where the data came from, what each variable means. So here, these are all different diamonds, the price of them, the carat, the color, the clarity, and then this lab variable is who like certified it or gave it the rating. And there's only 3. So this is another example where it looks like it's quantitative because the lab has a number, but there's only 3 labs. I wouldn't call that quantitative, I would call that categorical. There's only 3 categories it can fall into. So I went to Scatterplot. I did one quantitative variable, but multiple groups. So I have lab 1, 2, and 3, and I should have mentioned that all you have to do is copy paste. So I just copied everything for lab 1 and pasted it here, lab 2, lab 3. So here, the categorical variable has broken up the diamonds into the 3 different labs, and then the quantitative variable is how much the diamond costs. So we can see from these dot plots that lab 3 has the most expensive diamonds. They don't have any of these kind of cheaper, and by cheaper I mean still $1,000, but they don't have any of the cheaper diamonds, they have more of the higher priced diamonds. So we can use a dot plot, we could do the same thing with a histogram and kind of stack the histograms on top of each other. We could also do the same thing with a box plot, stack the box plots on top of each other. This way we can see, oh wow, look at this is so narrow, so lab 2 has lots of diamonds in this cheaper range as compared to labs 1 and 3. The one that wasn't included was a stem and leaf. So when we have one categorical variable and another quantitative variable, we can do dot plots, histograms, box plots, and the one that Scatterplot doesn't include is stem and leaf plots, where you have the two sets of leaves kind of opposite of each other. This was all in Unit 1. The only difference now is that they're like stacked so that you can compare, but even that we did in Unit 1. The new thing is two quantitative variables. So, two quantitative variables, I am going to look at the weather spreadsheet. This was weather data taken from Chapel Hill in North Carolina. We're going to compare temperature and humidity. So for that, I went to Scatterplot and did two quantitative variables. Surprise, surprise. So here's temperature as my explanatory, humidity as my response, and this is called a scatterplot. When you make a scatterplot, you have an x-axis and a y-axis. Your explanatory goes on the x-axis, your response goes on the y, and each of these data points represents one, in this case, one measurement, one moment in time. So we can see here at 1925, what is that, 7:25 p.m., all of this data was collected. And at that particular moment, the temperature was 86.9 degrees, the humidity was 42%. So that point gets plotted on the scatter plot. There it is. There's our data point. Okay, when you put them all together, you can see patterns. So what I'd like you to do now is pause the video and do a quick sketch. It does not have to look as good as this. Please don't spend 20 minutes doing individual dots. Just a rough sketch in your notes right here so that you have just a picture that you can refer to later. Okay, so it's not beautiful, but here's a quick sketch of what that scatter plot looks like. In the last unit, when we described distributions, we had four things we had to mention: center, shape, variability, and outliers. When we're looking at scatter plots, we still have four things we need to mention as we describe, but they're a little bit different. The first thing you should always mention is the direction. Direction can either be positive or negative. So in general, a positive direction is when x increases, so does y, which would look like this. As x gets larger and larger, y gets larger and larger. For example, as the temperature increases, ice cream sales go up. A negative direction would look like this. As x increases, y decreases. So as x gets larger and larger, y gets smaller and smaller. So positive, both variables are increasing. Negative, one is increasing while the other decreases. In this case, it looks like as the temperature rises, the humidity is going down. So this would be a negative direction. The second thing you have to include is form. In general, we can describe the form as linear or nonlinear. So a linear form would look like something that is approximately a line. A nonlinear form could look like a parabola, or it could look like exponential decay or exponential growth. I mean, it could be anything that's not linear. In our case, it looked like it was fairly linear. There's maybe a little bit of a curve here, but I would say that this is fairly linear. And this is kind of like the last unit where when we described like symmetric, you could say fairly symmetric. It's a similar idea here. The third thing you need to have is strength. The strength describes how closely the data points fit the pattern. So if we look at these points, I would say that this is moderately strong. A weak strength would look like, a cloud of points. There is maybe some kind of line, but it's not very strong. And then the last thing we need is any unusual features, anything you notice that is a little odd. For this example, like I said, there's these points over here that are curved, but other than that, no points that seem like outliers. Mostly we have a moderately strong, negative, linear pattern. Okay, I went through the data. I found some other stuff that I thought was interesting. You are more than welcome to look through and try this out on your own using the data and using Scatterplot. But just for some practice, here I have from the diamond sheet, this is the carat of each diamond and the price. So let's go through and just practice describing. The direction of this one is definitely positive. As the diamonds go up in carat, they also go up in price. So we have a positive direction. The form, there's maybe a little bit of a curve, but we could probably say that it's close to linear. I would say fairly linear. And strength, somewhere between moderate and strong. Any unusual features, it looks like we have a gap between 0.9 and 1 for some reason. There's nothing here, which is a little odd. I don't know if that's something about diamonds, that it's very rare to get like 0.95 carats, but that's one thing that we could maybe note. And then we could also note that there's 2 diamonds up here that are 1 carat but are much more expensive than the others. So I'd be curious, why are those 2 diamonds more expensive? Now, if it's frustrating to you to say somewhere between moderate and strong, you're not alone. If you're a math person and you really want some numbers and not words, don't worry, we will get to the numbers. There are ways that you can assess how strong or how linear a scatter plot is. For now, we're just kind of giving a general description. Don't get too hung up on what qualifies as moderate, what qualifies as strong or weak. You're just describing. Okay, now for this one, I used the tab, I think it's called like mammals or something, but it's got the gestation period, like basically how long each mammal, how long the pregnancies last, and then brain size. And in case you're curious, this is an elephant that has that massive brain. Makes sense. Okay, direction. The direction definitely seems positive. The longer the pregnancy, the bigger the brain in general. For form, I would say this doesn't look linear. It looks curved to me. It could almost be like exponential growth, or maybe half of a parabola. It's kind of hard to tell, but I would say with including this elephant, it doesn't seem linear. Even without the elephant, there's a slight curve here that I would say makes this not linear. The strength, moderately strong. Most of these points are fitting the pattern. There's a couple here that don't. Maybe these don't. This one, it kind of depends. If we're using that as part of our pattern, then that's definitely fitting the pattern. I would say they fit this nonlinear pattern with moderate strength. Yeah. Unusual features, we definitely say the elephant has an unusually large brain and gestation period compared to everyone else. And then we could mention, there's these 2 points here that seem a little off, and maybe these 4 that also seem a little off. We're not going to describe this one, I just wanted to bring it up. This is from the smoker tab. So we have age versus FEV, which I can't remember what does it stand for? Forced expiratory volume measures how much air a person can exhale during a forced breath. I wanted to bring this example up because you'll notice that there's no in-betweens for ages. You can't be 12 years and 2 months or 13 years and 5 months. It's just 12, 13, 14, 15. And I would say that age here could be a categorical variable. In fact, you might have to say like ages 3 to 6, ages 7 to 10, or something like that. We could analyze this and describe the direction, but because we only have certain values for age, it just seems to me like it's more of a categorical variable than a quantitative variable. Okay, so now to appease those of you who are upset about the lack of numbers. So we do have a way to measure both the direction and the strength of a scatter plot. And the thing that we use to measure is called the correlation coefficient. For whatever reason, it gets the letter R. I don't know why it doesn't get the letter C. I didn't make the rules. It is a unit-free measure, and like I said, it measures 2 things, direction and strength. So there's an applet here that I want you to just experiment with. Open it up. It's pretty easy to use. Try to answer these 4 questions below. Why don't you pause the video while you do that? Okay, so let's just look through these together. When you have 2 points, it doesn't matter where they are, correlation coefficient is either 1 or -1. And maybe you can already see the difference. 1 is when these points are kind of going in the positive direction, and -1 is when they're going in the negative direction. But just to summarize, it was either 1 or -1. If we put 9 points in the lower left-hand corner that have an R value or a correlation coefficient of about 0.9, and we add 1 more point to the top right, our correlation coefficient goes up. So in this case, it went from 0.9169 to 0.9695. Whereas if we put it down, our correlation coefficient, or R, went down quite a bit. So adding a point that fit the pattern made R increase. Adding a point that did not fit the pattern made R decrease. So maybe you can already tell at this point, but R is a value that has to stay between -1 and 1. If it equals -1 exactly, it is a perfect negative direction. If it equals 1 exactly, it's a perfect positive direction. The closer R is to 1 or -1, the closer the points are to fitting that pattern. So I'm going to start over here. Here's some points that are clearly moving in a positive direction, but they don't quite fit on a line. They have an R value of 0.8112. Now if I add some points further away from this pattern, pretty soon all we have is a cloud of points. There's no line here. And as you can see, the R value is getting closer to 0. There's no clear positive or negative direction here, it's just a cloud of points. When you have a cloud of points with no clear pattern, R is going to be close to 0. And here's just a quick example for the fourth question. Here's a curved shape, and R is about 0.7. Now if all I told you about a scatter plot was that R equals 0.7, your instinct would be to say, oh, 0.7 is close to 1, so that scatter plot must be pretty linear. Clearly that's not the case. R tells you about the direction and the strength, but you really need to see the scatter plot in order to understand if it's linear or not. So just a couple other things we need to know. Like I said, if R equals 0, then there's no linear relationship, it's just a cloud of points. You only want to use R for a linear relationship. As you just saw, it's a little misleading to use R if there's a curved pattern. So look at the scatter plot. If it looks like a line, then feel free to use R to describe the strength and the direction. There is a formula for calculating R. I will show you. It is on the formula sheet, the College Board formula sheet. It's right here. So it's 1 over n minus 1. This symbol means sum. And then this should look somewhat familiar. Taking a value and subtracting the mean and then dividing by the standard deviation is a z-score. So for each data point, you take the z-score for the x value times the z-score for the y value. You add them all up and then you divide by n minus 1. It's a lot of work. Most of the time you'll just be using technology to calculate R. And we'll get to that in a different video. For right now, don't worry about it. And then the last thing to remember is that correlation does not equal causation. I'm sure you've heard this phrase before. Just because you have a scatter plot with a clear linear pattern doesn't mean that the explanatory causes the response. This is my favorite example of that. The red line is showing the number of people who have drowned by falling into a swimming pool each year, and the yellow line is showing the number of films that Nicolas Cage has appeared in. Clearly we need to get him out of the movie industry so that we can save people from drowning in pools. So just because you have a strong positive association does not mean that X is causing Y to happen. There might be a variable lurking in the background that you don't know about. Okay, this last just example is for you to practice on your own. This is once more real data that I found on data.gov. The police in Bloomington, Indiana just kept track of the number of pedestrians and cyclists. Why don't you take a moment and answer the questions underneath this scatter plot. Pause the video and try that now. Okay, I would call this a positive, fairly strong linear relationship. So look, I just got through 3 of the 4 things. It's positive because as pedestrians increase, so do cyclists. Fairly strong and linear. It definitely looks like it forms a line, and I'd say fairly strong because they're pretty close to that line. All the dots are pretty close. So that's already 3 of the 4. The last thing was anything unusual. I would point out that there's one point that does not fit the pattern, and that's the day that there were almost 1,800 pedestrians, but only 600 cyclists. So perhaps a parade. Part B, does one variable make more sense as the explanatory? I would say in this case not really, because it's not like the number of pedestrians causes the number of cyclists. It's probably more like the weather influences both at the same time. If it's a nice day, there'll be more people walking and more people biking. So in this case, it probably doesn't make sense to have it either way. We should probably be tracking temperature versus pedestrians and temperature versus cyclists. And then C, a reasonable guess for R, somewhere around 0.75. Basically, you don't want to say 1 because this isn't a perfect line. The only time you would have an R value of 1 would be if every single point was on a line. And that's not the case here. You probably wouldn't want to say anything below 0.5 because 0.5 would be not a very strong relationship, and these I'd say are fairly strong. If I were grading this problem as a teacher, I would accept anything between 0.5 and 1, but I would not accept 0.5 and I would not accept 1. So somewhere in between, which is why I said 0.75, straight down the middle. So once again, this might be frustrating for those of you who really want more numbers and less words, and I promise we will get to that in the next couple videos. The whole point of making a scatter plot is so you can develop some kind of model and use that to predict future values, and that's what we'll get to in the next video.